Hello there, and welcome to Science into Sleep channel. Tonight we are drifting into the realm of black holes. These are the most extreme objects in the known universe, places where matter is crushed beyond recognition and light itself cannot escape. In this journey, we will wander through collapsing stars, bending space-time, invisible horizons, and the silent giants that sculpt entire galaxies. By the end, you may see darkness in a completely different way. If you enjoy these gentle journeys through science, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Space is full of light. Stars burn across every corner of the visible universe. Galaxies glow with the combined fire of billions of suns. And yet, woven between all that brilliance, there are places where light goes in and never comes back out. These are black holes. They are not holes in the traditional sense. They are objects, extremely dense, extraordinarily compact objects. A black hole forms when a massive star runs out of fuel and collapses under its own weight. The core falls inward so violently that nothing can stop it. Not the pressure of atoms, not the resistance of electrons, not even the rigid walls of neutrons. Everything gives way. What remains is a point of almost unimaginable density. Surrounding that point is a boundary, a border in space, beyond which escape becomes impossible. We call it the event horizon. It is not a wall. It is not a surface you could touch. It is simply the distance from the center at which the pull of gravity becomes stronger than the speed of light. Once something crosses that line, it is gone from our universe. No signal, no particle, no flash of light can return. Think of it like a river flowing toward a waterfall. Far upstream, you can still paddle back, but at a certain point, the current becomes too strong. You are carried forward no matter what you do. The event horizon is that point, and beyond it, the waterfall has no bottom. Black holes are among the simplest objects in physics. They can be described by just three properties: mass, spin, and electric charge. That is all. A black hole has no memory of the star it once was. It does not remember its chemical composition. It does not remember its temperature or its color. All that information is gone, reduced to 3 numbers. This strange simplicity is part of what makes them so fascinating. They are cosmic erasers. They take the rich complexity of a dying star and compress it into silence. You could say that a black hole is the universe at its most minimal. Nothing was wasted, nothing left over, just gravity, curvature, and emptiness. And from that emptiness, so much of the cosmos takes shape. To understand how a black hole is born, we first need to understand how a star dies. A star spends most of its life in balance. The outward push of nuclear fusion in its core fights against the inward pull of gravity. For millions or even billions of years, these two forces hold each other in check. The star shines steadily. It is calm. But deep inside, the fuel is running out. A star like our Sun burns hydrogen into helium. Larger stars continue fusing heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon, then silicon, and finally iron. Iron is the dead end. Fusing iron does not release energy, it absorbs it. So, when the core of a massive star fills with iron, the engine stops. Gravity, which had been patiently waiting, now wins. The outer layers of the star crash inward at a quarter of the speed of light. In less than a second, the core is squeezed to incredible density. If the original star was between about 8 and 25 times the mass of our Sun, the collapse halts at the neutron star stage. Neutrons resist being pushed closer together. A neutron star is born. It is about 10 kilometers across, yet contains more mass than the Sun. A single teaspoon of its material would weigh around 1 billion tons on Earth. Like carrying an entire mountain range in the palm of your hand. But if the star is heavier, even neutrons cannot hold. The collapse continues past every known limit. There is no force in physics strong enough to stop it. The matter keeps falling inward, and a black hole is formed. The boundary we talked about earlier, the event horizon, appears. From the outside, the collapsing star seems to freeze at that border. Light from its surface stretches and reddens. It fades. And then it is gone. The star has become something else entirely. Picture a room where the floor slowly gives way. First the furniture shifts, then the walls buckle, then the ceiling caves in. Everything in the room is drawn to a single point at the center. That is the singularity. Or at least, that is what our current equations predict. At the very center of a black hole, all the mass is thought to be concentrated at a point of zero volume and infinite density. This is singularity. It is where our understanding of physics breaks down. General relativity, Einstein's beautiful theory of gravity, produces infinite answers at the singularity. And in physics, infinity usually means we are missing something. The equations are telling us they have reached their limit. They need help. That help may come from a theory of quantum gravity, a framework that combines the physics of the very large with the physics of the very small. We do not have that theory yet, but singularity is one of the strongest hints that it must exist. Now, the event horizon deserves a closer look. Its size depends entirely on mass. For a black hole with the mass of our Sun, the event horizon would be roughly 6 kilometers across. A small city could fit inside it. For a black hole 10 times that mass, the horizon stretches to about 60 kilometers. And the supermassive black holes at the centers of galaxies can have event horizons larger than our entire solar system. The more massive the black hole, the gentler the crossing. This sounds strange, but it follows from math. Near a small black hole, gravity changes dramatically over short distances. You would be stretched and compressed in a process often called spaghettification. Your feet, being closer to the center, would be pulled much harder than your head. The difference in force would tear you apart long before you reach the horizon. But near a supermassive black hole, the gradient is far gentler. You could cross the event horizon without feeling anything unusual. No alarm, no flash of light, no barrier, just a quiet, invisible threshold. And yet, from the perspective of someone watching you from a safe distance, something very different would happen. They would see you slow down. Your movements would become sluggish. Your image would redden and dim. Time itself, from their point of view, would seem to stop for you at the event horizon. You would appear to freeze there forever, gradually fading into darkness. This is not an illusion. It is a real consequence of how gravity affects time. Clocks run slower in stronger gravitational fields. Near a black hole, this effect becomes extreme. Time bends. Light bends. Space itself bends. And that bending is the essence of what a black hole really is. Black holes do not simply sit in space doing nothing. They interact with everything around them. One of the most dramatic interactions happens when matter falls toward a black hole. Gas and dust do not usually drop straight in. They spiral, like water circling a drain. As material orbits closer, it forms a flat, spinning disk. We call this an accretion disk. Inside that disk, matter moves at tremendous speed. Particles collide, friction builds, temperatures rise to millions of degrees. The inner regions of the disk glow with intense radiation. X-rays, ultraviolet light, and sometimes visible light pour outward. A black hole itself emits nothing, but the material just outside the event horizon can become one of the brightest sources of energy in the universe. Imagine a dark whirlpool in the glowing sea. The whirlpool itself is invisible, but the water rushing around glows white with heat. That is what an accretion disk looks like. Some of the most luminous objects in the cosmos are powered by this process. Quasars, for instance. These are supermassive black holes actively feeding on vast amounts of gas. A single quasar can outshine an entire galaxy of hundreds of billions of stars, all from the energy released by matter falling toward an object you cannot even see. Now, not all the matter in an accretion disk falls in. Some of it is flung outward in powerful jets. These jets shoot from the poles of the black hole at nearly the speed of light. They can extend for thousands of light years, ploughing through the surrounding gas, heating it, pushing it aside. The mechanism behind these jets is still not fully understood. It likely involves magnetic fields twisted by the spinning space around the black hole. The rotation of the black hole itself drags spacetime along with it. This effect is called frame dragging, like a spinning ball placed in thick honey. The honey near the ball is pulled into rotation. Space near a spinning black hole behaves the same way. It twists. And anything within that twisted region is forced to move in the direction of the spin. This region is called the ergosphere. It sits just outside the event horizon. Inside it, staying still is impossible. You must orbit. Even light must orbit. And from this region, energy can actually be extracted. The physicist Roger Penrose described a process in which an object entering the ergosphere could split in two. One piece falls into the black hole. The other is flung outward with more energy than it started with. The extra energy comes from the rotation of the black hole itself. This is the Penrose process. It shows that black holes are not just consumers, they can also be engines. Now, there is another kind of energy release that is far more subtle. In 1974, Stephen Hawking proposed something remarkable. He showed that black holes are not entirely black. They radiate, very faintly, very slowly, but they radiate. This is Hawking radiation. It arises from the strange behavior of the quantum vacuum. Space, even empty space, is not truly empty. Pairs of particles and antiparticles constantly pop into existence and annihilate each other. This happens everywhere, all the time. But near the event horizon, something unusual can occur. One particle of the pair falls in, the other escapes. To an outside observer, it looks like the black hole just emitted a particle. Over time, this process drains the black hole of energy. The black hole slowly shrinks. It loses mass, and eventually, in theory, it evaporates completely. The timescale for this is staggering. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to evaporate. That is far longer than the current age of the universe. But for very small black holes, the process would be faster. And as a black hole gets smaller, it gets hotter. It radiates more intensely. In its final moments, it would release a burst of energy, a flash, then nothing. The black hole would be gone. Hawking radiation raised a profound question. If a black hole can evaporate, where does all the information go? Everything that ever fell in, every atom, every photon, every piece of a star, does it vanish? In quantum mechanics, information is never supposed to be destroyed. It can be scrambled, hidden, spread thin, but never erased. This conflict between general relativity and quantum mechanics is called the black hole information paradox. It remains one of the deepest unsolved problems in all physics. Let us widen our view. Black holes are not rare. They are everywhere. Our galaxy, the Milky Way, is thought to contain roughly 100 million stellar mass black holes. Most of them are invisible. They do not have accretion disks. They are not feeding on anything. They drift through space in silence, like dark stones scattered across an ocean floor. We only detect them when they interact with something: a companion star, a cloud of gas, a passing wave of gravitational energy. The first strong evidence for a black hole came in the early 1970s. An X-ray source in the constellation Cygnus was flickering. It was called Cygnus X1. Observations revealed a massive, invisible object orbiting a blue supergiant star. The invisible companion was too heavy to be a neutron star. It had to be a black hole. Since then, many more candidates have been confirmed. Some are found in binary systems, two objects orbiting each other, one visible, one dark. The visible star is slowly losing material to its invisible companion. Gas streams across the gap between them. It spirals inward. It heats up. It glows in X-rays. This is how we see the unseeable. Now, move to the center of nearly every large galaxy. There, something far more massive waits. Supermassive black holes. These are not formed from single dying stars. They contain millions to billions of solar masses. The one at the center of our own galaxy is called Sagittarius A star. It holds about 4 million times the mass of the Sun. And yet, it is quiet. It is not actively feeding on large amounts of gas right now. It is dormant. Picture a sleeping giant in the basement of a vast building. The building is the Milky Way. The giant is Sagittarius A star. It has been resting for a very long time, but we know it is there. Stars near the galactic center orbit it at tremendous speeds. One star, known as S2, completes its orbit in about 16 years. it reaches speeds of nearly 3% of the speed of light at closest approach. By tracking these orbits, astronomers Andrea Ghez and Reinhard Genzel confirmed the existence of the supermassive black hole. They shared the Nobel Prize for this work in 2020. Other galaxies have even more massive central black holes. The giant elliptical galaxy M87 has a black hole of nearly 6.5 billion solar masses. In 2019, the Event Horizon Telescope collaboration produced the first image of a black hole shadow. It was the one in M87. The image showed a bright ring of glowing gas surrounding a dark central region. That dark patch is the shadow of the event horizon. Light from behind the black hole is bent around it. Some of it reaches our telescopes. Some of it spirals inward forever. The ring shape is a direct consequence of gravitational lensing. Light travelling near the black hole is curved by the warped spacetime. Rays that pass just outside the event horizon are bent so strongly that they loop around the black hole before escaping. This creates a bright ring visible from every angle. Think of it like a glowing halo surrounding an invisible sphere. The sphere itself is pure darkness, but the halo tells you it is there. In 2022, the same team released an image of Sagittarius A star, our own galactic center. Smaller and more dynamic than M87's black hole, it was harder to capture. Gas moves around it so quickly that the image changes within minutes. But the result was unmistakable. Another ring, another shadow. Another confirmation is that Einstein's equations, written over a century ago, still hold true at the edge of the most extreme environments in existence. Gravitational lensing is not limited to imaging black holes. It also distorts the light from distant galaxies passing near any massive object. But near a black hole, the effect is absolute. Space is curved so deeply that photons travel in circles. At a specific distance, called the photon sphere, light orbits the black hole just like a planet orbits a star. But these orbits are unstable. The slightest disturbance sends the photon either inward or outward. It is a razor edge, a boundary of perfect balance that nothing can maintain for long. One of the most astonishing discoveries of recent decades is that we can hear black holes. Not with our ears, but with instruments sensitive enough to detect ripples in the fabric of space itself. These ripples are called gravitational waves. Einstein predicted them in 1916, but it took a full century before we had the technology to measure them. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a signal. It came from two black holes spiraling toward each other over 1 billion light-years away. Each one was about 30 times the mass of our Sun. They had been orbiting each other for millions of years, slowly losing energy, spiraling closer, moving faster. In the final fraction of a second, they merged. The collision released more energy than all the stars in the observable universe combined. Not as light, as gravitational waves. Ripples in space-time spread outward in every direction. When those ripples passed through Earth, they stretched and compressed space by an almost impossibly small amount, less than 1,000th of the width of a proton. LIGO caught it. The signal was a chirp, a rising tone that swept upward in frequency and then stopped. That stop was the moment of merger. Two black holes became one. A new, larger black hole was born, spinning rapidly, ringing like a struck bell before settling into silence. Since that first detection, dozens more have followed. Black hole mergers, neutron star collisions, even hybrid events where a black hole swallows a neutron star. Each detection reveals new details about the lives and deaths of compact objects. Gravitational wave astronomy has opened an entirely new window on the universe. Before LIGO, everything we knew about space came from light. Now we can listen to it as well. Picture a world where you could only see. Every piece of knowledge, every experience came from your eyes alone. Then, one day, you suddenly gained the ability to hear. A whole new layer of reality would open up. That is what gravitational wave detection has done for astronomy. Now, let us consider something strange about the way black holes grow. When two black holes merge, the resulting black hole has less mass than the sum of its parents. The missing mass has been converted into gravitational wave energy. This follows Einstein's famous relationship between mass and energy. The merger we detected in 2015 converted roughly 3 solar masses into pure gravitational radiation. 3 suns worth of matter turned into ripples in spacetime, gone from the material universe, existing only as a wave stretching through the cosmos. Black holes can also grow by swallowing gas over long periods. This is how supermassive black holes are believed to have reached their enormous sizes. In the early universe, shortly after the Big Bang, conditions were dense and chaotic. Gas was everywhere. The first black holes, perhaps formed from the collapse of the very first massive stars, began to feed. They grew. They merged with other black holes. They consumed surrounding clouds of hydrogen and helium. Over billions of years, they became the monsters we see today at the centers of galaxies. But there is a puzzle here. Some supermassive black holes appear to have formed surprisingly early. We see quasars shining brightly when the universe was less than 1 billion years old. For a black hole to reach 1 billion solar masses in that time seems difficult. Even if it fed continuously, there are limits to how fast it can consume gas. This maximum rate is called the Eddington limit. It describes the point at which the radiation from infalling gas pushes back against the incoming flow. The black hole's own light creates a kind of pressure that slows its growth. Like a fire that grows so large, its heat begins to push away the fuel feeding it. Several ideas have been proposed to solve this puzzle. One involves direct collapse black holes. Instead of forming from a dying star, these would have formed from enormous clouds of gas, collapsing directly into black holes without forming a star first. That would give them a head start. A seed black hole of 10,000 or 100,000 solar masses, rather than the 10 to 20 solar masses of a typical stellar remnant. Another idea involves periods of super Eddington accretion, brief episodes where the usual limits were exceeded. Gas poured in faster than radiation could push it out, perhaps through non-uniform flows or along magnetic funnels that bypass the radiation barrier. We do not yet know which path nature chose. Perhaps it used several. What we do know is that supermassive black holes have been shaping galaxies since the very beginning. There is a tight relationship between the mass of the central black hole and the properties of the galaxy surrounding it. Larger black holes tend to live in larger galaxies with faster moving stars. This correlation, known as the M-sigma relation, suggests that the black hole and its galaxy grow together. They influence each other. The black hole's feeding episodes release energy that heats the surrounding gas. This can slow star formation. It is a kind of cosmic feedback. The galaxy feeds the black hole. The black hole, in turn, regulates the galaxy. Like a thermostat in a building, when the temperature rises too high, the heater turns down. When it drops, the heater kicks on again. This cycle of feeding and feedback is one of the key processes shaping the large-scale structure of the universe. Without it, galaxies would look very different. Stars would form too quickly in some places and not at all in others. The universe we see today, with its mix of spirals and ellipticals, its clusters and voids, is partly a product of this delicate dance between black holes and the galaxies they inhabit. There is a curious idea at the intersection of black holes and information theory. It is called the holographic principle. It suggests that all the information contained within a volume of space can be described by data encoded on the boundary of that region. Like the way a flat hologram can create the appearance of a three-dimensional scene. When applied to black holes, this means all the information about everything that has fallen in may be stored on the event horizon itself, not inside, on the surface. The amount of information a black hole can hold is proportional to the area of its event horizon, not its volume. This is deeply strange. In everyday life, the amount of stuff that fits inside a box depends on the volume of the box. But for black holes, the boundary is what matters. This idea, developed by physicists Gerard 't Hooft and Leonard Susskind, has become a cornerstone of theoretical physics. It connects gravity, thermodynamics, and quantum information in ways we are still trying to fully understand. Jacob Bekenstein first proposed that black holes have entropy. Entropy, in simple terms, measures disorder, or more precisely, it measures the number of possible microscopic arrangements consistent with what we observe from the outside. Bekenstein realized that the entropy of a black hole is enormous. It is proportional to the area of the event horizon, measured in tiny units called Planck areas. Each Planck area is about 10 to the power of negative 66 square centimeters. Unimaginably small. And yet, the total number of these tiny patches on a black hole's horizon gives us the black hole's entropy. This was a breakthrough. It connected the physics of gravity to the physics of heat and information. Hawking's calculation of black hole radiation followed naturally from this insight. Together, Bekenstein and Hawking laid the foundations of black hole thermodynamics. Black holes obey laws that mirror the classical laws of thermodynamics. The zeroth law states that the surface gravity of a stationary black hole is constant across the horizon, like temperature being uniform in a body at thermal equilibrium. The first law relates changes in mass to changes in horizon area, spin, and charge, like conservation of energy. The second law states that the total area of all event horizons can never decrease, like entropy always increasing. And the third law states that you cannot reduce the surface gravity to zero in a finite number of steps, like the impossibility of reaching absolute zero. These parallels were initially thought to be just analogies, but Hawking radiation showed they were real. The surface gravity truly is a temperature. The area truly is an entropy. Black holes are genuine thermodynamic objects. They are the hottest objects in the universe when they are small, and the coldest when they are large. Now, let us step into even stranger territory. What happens at the very end of a black hole's life? As it evaporates through Hawking radiation, it shrinks. The temperature rises. The radiation grows more intensely. Eventually, the black hole reaches a mass comparable to the Planck mass, about 22 micrograms. At this point, both quantum mechanics and gravity are equally important. Our current theories can no longer be trusted. We simply do not know what happens next. Does the black hole vanish completely? Does it leave a tiny remnant? Does it explode? These questions are unanswered. They live at the frontier of physics. Some theorists believe that the final evaporation releases all the stored information in a burst. Others suggest the information leaks out gradually during the evaporation process, encoded in subtle correlations between the emitted particles. This is sometimes called the Page curve, named after physicist Don Page. He showed that if information is preserved, The entanglement entropy of the radiation should follow a specific curve. It should rise during the first half of the evaporation, then it fall during the second half, returning to zero when the black hole is gone. Recent theoretical work using tools from string theory suggests the page curve may indeed be correct. This would mean information is not lost. It is merely very difficult to recover. Scrambled across countless particles of Hawking radiation, like tearing a book into confetti and scattering it across a field. The information is still there, but reading it would require collecting every single piece and reassembling the whole. Another fascinating frontier is the connection between black holes and quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a bold idea. They suggested that entangled particles, pairs connected by quantum correlations, might be linked by tiny wormholes, bridges in space-time. This idea is often summarized as ER equals EPR. ER refers to Einstein-Rosen bridges, the technical name for wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox, a foundational thought experiment in quantum entanglement. The proposal implies a deep unity between the geometry of space and the structure of quantum information. If it is true, space-time itself may be woven from entanglement. The fabric of the cosmos, the very stage on which everything happens, might be stitched together by quantum connections. This is a breathtaking idea. It suggests that black holes are not just exotic objects at the edges of our understanding. They may be windows into the fundamental nature of reality itself. Let us visit one more quiet mystery before our journey begins to close. It involves the interior of a black hole. What is it like inside? From the outside, we can observe the event horizon, the accretion disk, the jets, the gravitational lensing, but the interior is hidden, completely and permanently. No signal from inside can reach us. General relativity tells us that once you cross the event horizon of a non-rotating black hole, every direction leads inward. There is no turning back. Not because of speed, because of geometry. The center of the black hole is not a place in space. It is a moment in time. You cannot avoid it any more than you can avoid next Tuesday. For a rotating black hole, the interior is even stranger. The singularity is not a point. It is a ring. And mathematics suggests the existence of other regions of space-time beyond it. Passages to other universes, perhaps, or to distant parts of our own. These solutions are mathematically valid, but most physicists believe they are physically unrealistic. Small disturbances would destroy the delicate structure needed for such passages. The interior of a real rotating black hole is probably far more chaotic than the idealized equations suggest. Still, the possibility lingers. It whispers from mathematics like a half-remembered dream. We cannot go there. We cannot check. And perhaps that is what makes it so alluring. We have travelled a very long way tonight, from the death of a star to the birth of a black hole, from the quiet edge of the event horizon to the roaring collision of merging giants, from the ghostly glow of Hawking radiation to the deep questions about information, entropy, and the very fabric of space. And through it all, one thing keeps returning: silence. Black holes are, above everything, quiet. They do their work in darkness. They shape galaxies without a sound. They bend light and time without a whisper. And maybe that is what makes them the perfect companions for a night like this. You have been breathing this whole time, gently, steadily. Your body knows what to do. If you enjoyed this journey, you might like to explore another before sleep fully arrives. And if you feel like it, liking or subscribing helps others find their way here as well. Let your thoughts settle like dust after a long walk. There is nothing left to figure out tonight. The questions can wait. The universe will still be there in the morning. All those invisible giants quietly spinning at the centers of distant galaxies will keep doing what they do, and you can rest. Sleep well, and good night.